Hey everyone, today's topic for Coding++ is pathfinding, specifically A-star pathfinding. This algorithm is quite popular for games where real-time pathfinding is needed, like for example real-time strategy games. I've used it in cookies too, which I'll show later in the video. So the algorithm. Here we have a 10 by 10 grid where the black parts are obstacles. The starting position is marked in red and the goal is marked in green. We'll have an array in which we'll place new open tiles from the map. The first tile is the starting position. Every tile has its cost value. It is a sum of the distance from the goal tile and the distance we have traveled since the start tile. The travel cost values are usually 14 for going diagonally and 10 for everything else. Then we do the following. From the array we pick an open tile that has the least cost. Then mark that tile as a closed tile, and for every tile around the tile we picked, we'll mark it as open and calculate its cost. All of the newly opened tiles will also point to the tile they came from. I'll show an example so that everything I just said makes more sense. So here we have our example map. As I said, the black parts are the obstacles, the red part is the starting position, and the green part is the end position. So we add this starting position tile to our array. Since the starting position is not the end position, there's no need to calculate all of the cost values. So we'll open all of the surrounding tiles to this tile. Here we have all of the tiles. As you can see, they all point to the tile which they came from. And here they have their cost values. So as you can see, this number in the top left marks the cost value from the start position. As I said, it is 14 when going diagonally and 10 for everything else. And this top right number is basically the distance from this green node. You can easily calculate that by using Pythagoras theorem. And this big number in the middle is just simply a sum of these two values. So our program is going to pick the lowest cost value next. In this case, this is 70, and then it's going to open this tile. As you can see, it opened the new nodes surrounding this tile. And then here we have a few 74s. We're going to pick the one that is closest to our green tile, so that would be this one. So then we have these two 78s, we have also this one. This one is the closest. As you can see, it says 44, so we'll open that one. Then we'll open these two. And as you can see, it just continues like that. So next up we have, I think, 83, then we have 85 here, and then we have a few 88s. We'll open this one since it's the closest one. Oh, this 86 is actually here. So we'll open this 88 here, and we have another 88, and we have another 88, and we've reached our end node. Since, as you can see, all of the arrows are pointing to the previous direction, we can just go back and create a path. And that's basically how the algorithm works. So now I'll show it on some bigger maps, since that is where it's more interesting. In this example, you can also see all of the open and closed nodes as the algorithm goes and searches further. One cool thing that we can do is, instead of finding the tile with the least cost, we can find the tile with the most cost, and then we get a path like this. we will take a look at the source code of this project, which is available on my GitHub page. The link to that will be in the description down below. So first of all, we define the start and end point, and we load the map. The map is just a simple image. Then from the map we find the red and green pixel, and we mark those as a start and as an endpoint. After that we simply call the a star function, which we'll get to in a moment. It asks for the map as a parameter for the start point, the end point, and the color of obstacles. The return type are basically directions like left, up, right, top, left, and so on. Then after that we just have some visualization so that the things look like this once they're calculated, as you can see. So let's get to the a star. So this is the function, and first of all I define all of the directions. There are 8 of them in this case. You can define 4 of them, so then the algorithm won't be able to move in. The algorithm won't be able to move diagonally. Then we'll define a node or a tile. Every tile has a direction, it has its start distance cost, end distance cost, and its position, and also it can be either open or closed. Closed tiles are basically ones we've processed already. And also we have here our directions, so this is basically the format that this function will return. We add the starting node to the end of the array. We set its position, its cost, and here we have the node ID. This is basically the node that we're going to process. So we enter a while loop, and this basically goes on forever until we either find a path or we cannot open any more tiles. So here we have a pointer to the target node that we're going to be processing. Then we have here a for loop that goes for each of the 8 directions that we can go in. First of all, we'll close the target node. We'll calculate the position of the new node that we might open, depending on whether it's already open. We check if this position is out of bounds. We check if it's an obstacle, in which case we just continue and we don't open anything. Then we check if the node already exists in the array that we specified earlier. If it exists, we will try to update it with a lower cost if that is possible. So we check if it's the same position, and then if it's also open, it must be open for us to update it. We can check if it's diagonal, in which case we will check if we can set it a lower cost value. If that's the case, then we also have to change where it's pointing. In the case where the node does not already exist, we add a new node to the end of the array. We have to keep in mind that since we resized a vector, all of the pointers to that vector will become invalid. So we have to point to the new address of our target node. And then this node.back is basically the last node that we added. So this node that we added here, we set its position, its direction. We also check if it is the endpoint. We'll skip over that. We'll come back to that in a moment. Then we also calculate all of the cost values. As I said, if we're going diagonally, which is in this case I is bigger or equal to 4, then we add 14. Otherwise, we add only 10. We also need to calculate the distance from the endpoint, and we calculate that and save it to the end distance cost. And that's it for this for loop. That's everything there is. After we've added all of the nodes, we have to pick the next node that has the lowest cost value that we will open next. So here we have a few variables. This is the node that we will pick. This is the cost value of that node, and this closest variable is here specifically if multiple nodes have the same cost value, then we'll pick the one that is closest to the end node. So we go through all of the nodes. If it's not open, we make sure to not select that one no matter what. And then we check if we basically just find the node that has the lowest cost. And after this whole for loop, we have our node with the lowest cost. If for some reason this is -1, then basically we opened all of the nodes and, well, there is no path to our target location. We will break and it will return an empty vector. Otherwise, we set our node ID to the minimum value that we found, and we continue on, and basically we do it until, as I mentioned here, until we add a node that has the same position as the goal position. And then after that, after we do that, we create a vector of directions. This is basically the vector that will return. We start from the end position, and then we start pushing back all of the directions that we have to go in to get back to the start node. Since we're starting from the end point, we'll also have to reverse this vector before we return it. And this basically goes through all of the nodes, finds a non-open node, and if its position is what we need, then we push its direction, we change our current position, and we do it until we get to the start point. And well, yeah, that's pretty much it for this algorithm. It's not all that complicated, especially once you understand exactly what happens. So as I said, I'm using this algorithm in Cookies 2 for pathfinding. My version is slightly modified version of this algorithm, since sometimes I do not need to use the whole pathfinding system. I can just send units in a straight line. Also, units avoid walls in most cases. That is simply there because units used to get stuck really easily on walls when going diagonally. The algorithm also uses another thread so that the main game won't be interrupted. Since if you, for example, select multiple units and send them somewhere, then it would take a lot of time to calculate all of the paths, and so the second thread just does one by one in the background. But yeah, that's pretty much it for this video. I hope you learned something new. And yeah, that's it. Thanks for watching, and until the next one.